Today, we're really excited to invite you into the joy of architecture. We're going to tackle something absolutely fundamental for modern software.
Yeah, we're talking messaging protocols in distributed systems. Really foundational stuff.
Exactly. And we've got a great stack of sources for this deep dive. Everything from really dense technical specs to, real-world case studies. Think companies like Netflix, Uber.
Big players who live and breathe this stuff.
Right. So our mission today is to kind of distill all that, unpack it, help you really get the design philosophies, the trade-offs, the best places to use these protocols.
So you can walk away feeling, genuinely well-informed, ready to actually apply it.
Okay, so let's unpack this. Distributed systems. We're talking about separate pieces needing to talk to each other.
Yeah.
Reliably, without bringing the whole thing down if one part hiccups.
That's the core challenge, absolutely. And it really fundamentally starts with a shift in thinking, moving away from synchronous communication towards asynchronous.
Okay, what's the key difference there?
Well, synchronous, as our sources point out, it's like making a phone call. You call, you wait for an answer. If the other side is slow or busy, you're just stuck, waiting.
Creates tight dependencies then, bottlenecks.
Exactly, rigid dependencies. It causes ripples if one service slows down. But asynchronous, that decouples the sender and receiver. The sender just fires off the message and moves on.
Doesn't wait for the response.
Right. Which allows for independent scaling, much better fault tolerance. It naturally leads to something called eventual consistency, where things sync up over time, but the system stays responsive.
Okay, so in that async world, there are common ways messages actually flow, right? Patterns.
Precisely. We mostly see two main patterns pop up again and again. First, there's queuing, sometimes called point-to-point.
Okay.
Messages go into a sort of buffer, a queue, and then a single consumer pulls a message off and processes it. It's perfect for distributing workload, like processing tasks one by one.
Makes sense. One worker, one task.
Yeah. Then there's publish-subscribe, pub/sub for short. Here, messages get sent to a named topic. Think of it like a channel. And then potentially many subscribers can listen to that topic and get a copy of the message.
Oh, okay. So that's more for broadcasting information.
Exactly. Great for event notifications or fanning out data to multiple different systems that all need to react to the same event happening.
And to manage all this message flow, especially asynchronously, there's usually a piece of infrastructure in the middle, isn't there?
That's where the message broker comes in. Or message-oriented middleware, MOM is another term you'll hear.
Right, the broker.
Think of it like a central post office for your application's data. Producers send messages to the broker, and the broker reliably routes them to the consumers. It handles temporary storage, ensures messages don't get lost.
So it adds reliability.
A lot of reliability. And the sophisticated ones do much more. Advanced routing rules, transforming messages on the fly, handling transactions, security and management tools. It's a whole platform.
And this enables different ways of sending messages.
Yeah. Fundamental patterns, like unicast, that's one-to-one, multicast, one-to-many specific receivers, and broadcast, which is one-to-all interested listeners.
Okay, that clarifies the why and the what's. Let's peel back another layer. The message itself. What's it actually made of? Every message has a structure, right?
Absolutely. It's pretty standard, usually. You've got two main parts, a header and a body, or payload.
Header and body. Got it.
The header contains all the metadata. Things like a unique message ID, a timestamp, maybe priority, and crucially, routing information where it's going, where it came from.
And the body.
That's the actual application data, the stuff your service actually cares about. Now, how this looks on the wire, the actual bytes sent, that varies.
Oh.
You have text-based protocols. Stomp is a good example. They're human-readable, which is great for debugging, right? You can just look at the traffic.
That's probably less efficient.
Generally, yeah, more verbose. Then you have binary protocols. Kafka's native protocol is a prime example here. Highly optimized for performance. Compact, machine-readable formats. Less overhead.
And inside that body, the actual data, they can be formatted differently too.
Exactly. Common formats you see are JSON and XML. Again, human-readable, widely supported, but can be a bit bulky.
Right.
Then for more efficiency, or when you need strict schemas, you see binary formats like protocol buffers, protobuf, or Avro. They're much more compact.
And this leads to cloud events. You mentioned that. What's the deal there?
Yeah, cloud events is really interesting. It's a specification trying to bring some order to this. It defines a standard set of metadata attributes like id, source, type, spec version.
Okay, standard metadata.
Exactly. It creates a common envelope for any event data. So regardless of whether your payload is JSON or protobuf or what transport protocol you're using underneath, the infrastructure can understand these common header fields.
Ah, so it helps systems talk to each other more easily, interoperability?
Precisely. It lets infrastructure route or filter events without needing to understand the specific business data inside the payload.
Hmm.
Big win for interoperability.
Okay, this is where things often get really tricky for architects. Delivery guarantees. How do we actually know our messages get where they're going
Yeah.
and, like, processed correctly?
Yeah, this is super critical. And one thing you really have to keep in mind is that the guarantee isn't just about the protocol itself. It's a property of the entire system working together. Producer, broker, consumer, the whole chain.
Right, the whole system.
We usually talk about three main levels. First, at most once.
At most once.
Means the message gets delivered maybe once, maybe not at all. It might get lost. But crucially, it will never be duplicated. Think fire and forget.
Okay, when would you use that? It seems risky.
It's fine for non-critical stuff, maybe telemetry data, sensor readings, where losing one occasionally isn't the end of the world. Low overhead.
Got it. Next level.
At least once. Here, the system guarantees the message will be delivered. It won't get lost, but it might get delivered more than once. Duplicates are possible.
Okay, so no data loss.
Yeah.
But potential duplicates.
Exactly. This is very common. It's robust. But the key is your consumer application has to be ready for duplicates. It needs to be idempotent.
Idempotent, meaning?
Meaning processing the same message multiple times has the exact same result as processing it just once. Maybe you track message IDs you've already processed, for example.
Okay, requires careful design on the consumer side. And the third level?
The Holy Grail. Exactly once. The message is delivered precisely one time and processed precisely one time.
That sounds ideal, but difficult.
Notoriously difficult in distributed systems. Really hard.
Hmm.
Kafka has made some big strides here, though. They combine features like an idempotent producer with transactional APIs.
How does that work?
It allows the consumer to do its business logic and commit its read offset back to Kafka as a single atomic operation, so either both succeed or both fail and roll back. It prevents processing without committing or committing without processing. Huge for data integrity.
Wow, okay. That's complex but powerful.
Yeah.
So messages get there, but how do they know where to go in the first place? Routing?
Right. The routing mechanisms vary a lot, too. The simplest is probably direct or topic-based routing.
Like in Kafka and Nats?
Exactly. Producers send to a named topic. Consumers subscribe to that topic. The broker's role in routing is pretty minimal. It just delivers messages for the topics people ask for.
Straightforward.
Then you get more sophisticated stuff like content-based or rule-based routing. AMQP 0.9.1, which RabbitMQ uses, is the classic example.
How's that different?
Messages don't go straight to a queue. They go to an intermediary called an exchange. Think of the exchange as a smart router.
Okay.
The exchange looks at rules, called bindings, and maybe properties on the message itself, like a routing key in the header. Based on these, it decides which queue or queues the message should go to.
Ah, so the broker is much smarter about routing.
Much smarter. Different types of exchanges offer different routing algorithms, direct match, fan out to all queues, topic-based pattern matching. It allows for really flexible and complex topologies.
And the third type, you mentioned brokerless.
Right. Brokerless routing. This is the ZeroMQ approach. There is no central broker handling routing. The logic is embedded directly in your application chain using specific socket patterns.
So the application itself figures out where to send messages.
Essentially, yes. You define the network topology, who connects to whom, directly in your code. Very different philosophy.
Definitely. Okay, one last crucial foundation. Security. Can't forget that. How do we keep these messages safe?
Absolutely essential. It's multi-layered, really. First, you've got transport layer security, usually TLS SSL, that encrypts the connection itself. Protects against eavesdropping while messages are in transit.
Standard stuff for network connections.
Pretty standard, yeah. Then there's authentication, verifying who the client actually is. Is this application allowed to connect?
How's that done?
Could be simple username password, could be client-side TLS certificates, or more robust mechanisms using SESL simple authentication and security layer. That supports various pluggable methods like Scram or Kerberos for secure credential handling.
Okay, so we know who they are.
Yeah.
Then what?
Then authorization. Okay, you're authenticated, but what are you allowed to do? Can you publish to this topic? Can you subscribe to that queue?
Permissions.
Exactly. Usually managed via access control lists, ACLs, defined per user, per topic, per queue, whatever the broker supports.
Right. Is that it?
One more layer, potentially. message level security. This is end-to-end encryption, E2EE.
Encrypting the message body itself.
Precisely. The payload is encrypted by the producer and only decrypted by the final consumer. So even if the transport, TLS, is compromised, or someone inspects messages sitting on the broker, the actual content is still protected.
That sounds really secure.
It is. Emerging standards like MLS messaging layer security are working on making this efficient and scalable, especially for group messaging.
Okay, that covers the foundations really well. Let's dive into the big players now, the actual protocols. First up, AMQP, Advanced Message Queuing Protocol.
Right. AMQP Open Standard came out of the financial sector, so reliability and interoperability were key drivers. But the first thing to know, and it trips people up, is the schism between AMQP 0.9.1 and 1.8.
Schism. They're different.
Completely different, not backward compatible. Think of them as two protocols sharing a name.
Okay, so 0.9.1.
AMQP 0.9.1 is what RabbitMQ famously implements. It defines a very prescriptive broker model. The standard dictates server-side entities, exchanges, queues, bindings.
The smart broker idea we talked about.
Exactly. Producers publish to exchanges, exchanges route intelligently to queues based on bindings, consumers pull from queues. The broker does the heavy lifting for writing. Dumb clients, smart broker.
And AMQP 1.0.
1.0 is an OASIS and ISO standard, but it was a complete redesign. It only defines the peer-to-peer wire protocol, how bytes go over the network for transferring messages.
It doesn't define the broker part. Nope. Deliberately omits it. It focuses purely on connections, sessions, links. This makes it super interoperable at the protocol level, but it pushes all the messaging semantics, the queues, the exchanges, the routing logic onto the specific broker implementation.
So different vendors could implement 1.0 very differently.
Exactly. The protocol ensures they can talk, but the features depend on the broker.
Interesting split. Okay, next, MQTT, the IoT workhorse.
MQTT, yeah. Another OASIS standard, purpose-built for constrained environments. Think low-power devices, flaky networks, minimal bandwidth.
Like sensors out in a field.
Perfect example. It's a simple, very lightweight binary protocol. Tiny 2-byte fixed header uses a centralized broker with a publish-subscribe model.
And it's evolved too, right? V3 versus V5.
Big jump from MQTT v3.1.1 to v5.0. Version 5 added a lot of maturity needed for modern IoT, better error reporting using reason codes, more control over sessions with things like clean start and session expiry interval.
More control. Yeah, and richer metadata using user properties on messages. Native support for request response patterns, shared subscriptions so multiple consumers can load balance a topic, even topic aliases to save bandwidth. It really grew up.
What are its core features people rely on?
Well, the broker, obviously. Clients connect to it. Hierarchical topics with wildcards, which are super flexible for subscriptions. 3 quality of service levels, 0, 1, and 2, mirroring the guarantees we discussed.
At most once. At least once. Exactly once.
Right. Plus retained messages, where the broker keeps the last message on a topic for new subscribers. And the crucial last will and testament, LWT.
Last will.
Yeah. A client pre-registers a message with the broker. If the client disconnects, ungracefully loses power, network drops, the broker publishes that last will message, letting other systems know it died unexpectedly. Really useful in IoT.
Very clever. Okay, moving on. Stomp. Simple text-oriented.
Simple or streaming text-oriented messaging protocol, Stomp. It was designed with scripting languages in mind, and it's very deliberately modeled on HTTP.
Text-based, then.
Yep. Frame-oriented, you have a command like connect, send, subscribe, then headers, key value pairs, then an optional body, and a null byte terminator.
Simple sounds good.
Its strength is simplicity, easy to implement, easy to debug, because it's just text. And that simplicity makes it a fantastic fit for WebSockets.
For talking to browsers.
Exactly. Enabling real-time bidirectional communication between a web server and a browser. Stomp over WebSockets is a very common pattern for real-time web UIs.
Makes sense. Now, Kafka. It's huge, but its protocol isn't a standard.
Correct. The Kafka protocol is not an open standard like AMQP or MQTT. It's a custom, high-performance binary protocol specifically designed for Apache Kafka's unique architecture.
Which is?
A distributed, partition, append-only log. The protocol is request response over TCP, but heavily optimized for throughput by batching messages together.
And the architecture is different too. Dumb broker.
Exactly. Kafka brokers are relatively dumb. Their main job is efficient, durable logging, storing the data. The clients are smart. They handle partitioning, consumption logic, offset management.
Partitions. That's key to Kafka, right?
Absolutely. Topics are split into partitions. That's the unit of parallelism and also ordering. Ordering is guaranteed within a partition, but not across different partitions of the same topic.
Okay.
Producers decide which partition to write to, often based on a message key. Consumers in a group track their own progress independently for each partition using offsets, and all protocol requests are versioned for smooth upgrades.
Purpose-built for that log architecture.
Got it.
How about NATS? Heard it's fast.
NATS is definitely known for speed. It's a CNCF project. Performance, scalability, and simplicity are its mantras. Uses its own simple, text-based protocol.
Does it have different modes?
Kind of. There's core NATS. That's the original super-fast, in-memory, at-most-once pub subsystem. Great for ephemeral messages, service discovery, fire-and-forget stuff. Blazing fast.
In memory, so no persistence there.
Not in core NATS, no.
Yeah.
But then there's Jetstream. That's an optional persistence layer built right into the NATS server.
So Jetstream adds the reliability.
Exactly. Jetstream adds at least once and exactly once guarantees, message replay, durable subscriptions. It layers the durability on top of the core NATS performance. Its lightweight commands contribute to keeping things fast, even with persistence.
Interesting layering. Okay, last one on the list, ZeroMQ, the outlier.
Absolutely the outlier. ZeroMQ to EMQ is fundamentally different. It is not a message broker.
Not a broker. What is it then?
It's a messaging library, a toolkit you embed in your application. The Zero suggests zero broker, zero latency, zero admin.
So no central server.
No central server. Developers use the library to create direct peer-to-peer connections between application components using different socket patterns.
Like building your own network topology and code.
Precisely. It provides patterns like request-reply, publish-subscribe, push-pull. Underneath, it uses its own protocol called ZeroMQ. It's a completely different architectural choice.
Trading broker features for direct control and speed.
That's the core trade-off. Standards like AMQP or MQTT versus purpose-built optimization like Kafka versus this brokerless direct communication library like ZeroMQ. Very different philosophies.
Wow, that's a great tour of the major players. So how do they actually stack up? If you're an architect, how do you compare them?
Well, looking at a comparison matrix helps. Our sources lay one out across key dimensions: architecture broker versus brokerless, primary patterns, pub sub, queuing, delivery guarantees, ordering, persistence, routing smarts, performance, scalability, security, ecosystem maturity.
And patterns emerge quickly.
Definitely. You immediately see that Kafka dumb broker versus RabbitMQ smart broker distinction, or the lightweight nature of MQTT versus the complexity of AMQP, or ZeroMQ sitting off on its own as brokerless.
Let's talk performance again. Latency versus throughput.
Right, the constant tension.
How do they compare broadly?
Okay, broadly. Kafka is king of throughput. Millions of messages per second. Latency is decent, low milliseconds, but throughput is its main game. NATS aims for both ultra-low latency microseconds or even nanoseconds for core NATS and high throughput. Very performant all around.
RabbitMQ.
RabbitMQ AMQP generally prioritizes low latency for individual messages and reliable delivery over massive bulk throughput. Good for transactional workflows.
And ZeroMQ.
ZeroMQ gives you the absolute best raw performance, lowest latency microseconds, and potentially highest throughput precisely because it cuts out the broker middleman.
But performance depends on the breaker for MQTT and Stomp.
Heavily depends on the broker implementation, yes. And always be critical of benchmarks. Look at the why behind the numbers, the architecture.
Makes sense. What about scaling and reliability? More trade-offs?
Always trade-offs.
Yeah.
Kafka and NATS scale horizontally really well, add more nodes, but scaling Kafka by adding partitions isn't trivial. Rebalancing data can be disruptive.
Okay.
RabbitMQ scales with clustering mirrored queues for high availability. ZeroMQ scales naturally because it's decentralized, but managing that scale, topology, service discovery, that's all on you, the developer.
And reliability impacts performance.
Almost always. Stronger guarantees mean more overhead. Kafka's AXAL, wait for all replicas to confirm, is slower than AX1. MQTT, QoS2 is slower than QoS0. You pay for certainty and latency, no free lunch.
Absolutely. Okay, let's connect this to the real world. Where do these protocols actually shine? Use cases.
Right, this is crucial. The choice has to be driven by what your application needs.
So IoT edge computing.
MQTT dominates here. Lightweight, pub sub, that last will and testament session handling, perfect for tiny devices on shaky networks. And MQTT-SN goes even further for non-IP networks like Zigbee, using topic IDs instead of full strings to save every byte.
Makes sense. Microservices. event-driven stuff.
Here you see more variety. RabbitMQ, AMQP, is strong when you need complex smart routing. Intelligently sending an order-placed event to inventory, billing, and shipping services may be based on rules. Great for work queuing, too.
Right.
NATS is often chosen for general service-to-service chat because it's simple, fast, and has good request-reply support.
And Kafka.
Kafka is often the event backbone, the central nervous system, especially in event sourcing patterns. It provides that immutable, replayable log of everything that happened, the system of record.
What about just massive data pipelines, log aggregation?
Apache Kafka again. That's its original sweet spot. Its partitioned log can ingest insane volumes, logs, metrics, click streams with high throughput and durability. Multiple different teams or systems can then consume that same data independently.
Like the Netflix example.
Exactly. Their Keystone pipeline uses Kafka to process trillions of events daily for real-time recommendations. It shows Kafka's power as that high-throughput, durable event backbone.
Financial services. Transactions.
AMQP, RabbitMQ, often preferred here. Its focus on reliability, transactional integrity, message acknowledgements, and audible flows is critical when you absolutely cannot lose a message or process it incorrectly.
And that high-performance niche, HPC, inter-process communication.
That's ZeroMQ's territory. Brokerless means minimal overhead, perfect for lightning-fast communication between processes, maybe even on the same machine, IPC.
So a key takeaway seems to be understanding the job before picking the tool, like event log versus work queue.
Absolutely critical distinction. Kafka is an event log. It stores history. RabbitMQ is a work queue. It distributes tasks. Using Kafka as a simple task queue can be painful. It lacks features like prioritizing tasks or easily handling messages that consistently fail. Poison pills.
Right, tool for the job, avoids operational headaches.
Big time. Understanding that fundamental difference saves a lot of grief.
This leads naturally to that big architectural fork in the road. Broker-based versus brokerless. Huge implications, right?
Massive. It affects almost everything about how you build and operate the system.
So broker-based. Kafka, RabbitMQ, NATS.
Right. Everything talks through a central intermediary, the broker.
Yeah.
The diagram usually shows spokes connecting to a hub.
Advantages.
Loose coupling, services don't need to know each other's locations, centralized management, monitoring, built-in reliability features like persistence, guaranteed delivery. The broker handles a lot for you.
Disadvantages.
The broker is a potential single point of failure, even if clustered. Extra network hop adds latency. And crucially, managing the broker cluster itself can be complex and operationally expensive.
Okay. And brokerless, ZeroMQ.
No central hub. Applications use the library to connect directly, peer-to-peer. The diagram shows peers connecting directly to each other.
Yeah, advantages there.
Raw performance. Microsecond latency, huge throughput by cutting out the middleman. Simpler deployment, just include the library. Lots of architectural flexibility in how you connect
It
things.
sounds great, but what's the catch?
Big catches. Tighter coupling peers often need to know network addresses, requiring separate service discovery mechanisms. Management is decentralized, harder to monitor globally. And the biggest one. Reliability is entirely your problem.
Meaning?
Persistence, guaranteed delivery, queuing for offline peers, handling slow consumers. You have to code all of that into your application logic. ZeroMQ itself won't save messages if a receiver isn't ready.
So it's offloading complexity from operations to development.
Precisely. You don't eliminate broker functionality like reliability, you just shift who implements it. If you choose brokerless, you absolutely must budget the significant engineering time to build those reliability features yourself.
Huge trade-off. Okay, looking ahead. What's new and exciting in messaging? What's emerging?
Always evolving. Key drivers are still performance, security, interoperability. We mentioned MQTT for ultra-constrained devices.
Right, topic IDs.
Then there's QUIC-based messaging. This is a big deal. QUIC, built on UDP, underlies HTTP3.
Why is it good for messaging?
Several reasons. Faster connection setup, often zero RTT, zero round-trip time. It multiplexes streams over one connection, eliminating head-of-line blocking. Crucially, it supports connection migration switch from Wi-Fi to cellular without dropping the connection. Huge for mobile IoT. Plus, built-in TLS 1.3 encryption.
So we'll see protocols run over QUIC.
Yep, MQTT over QUIC is already emerging. Combines MQTT's strengths with QUIC's robust transport.
And cloud events, you mentioned that for interoperability.
Yeah, CloudEvents standardizes the metadata envelope around the event data. Decouples the event's meaning from the specific payload format or transport protocol. Makes it easier for different platforms and services to understand and route events without deep inspection. Google Cloud Run, Dapper, Native, all leverage it.
So the future looks more modular. Pick and mix.
I think so. You might pick QUIC as your transport, wrap your data in a Cloud Events envelope, and maybe use MQTT or NAT semantics on top. Decoupling the layers gives you flexibility. We're also seeing research in advanced security like post-quantum crypto for E2EE.
Fascinating. Let's look at how the big companies actually use this stuff. More real-world examples.
Yeah, case studies are super valuable. We talked about Netflix's Keystone using Kafka as that massive event backbone. Trillions of events, driving personalization, classic Kafka use case.
And Uber. They seem more mixed.
Uber is a great example of polyglot messaging, using different tools for different jobs. Their dispatch system, Disco, uses Kafka via REST APIs for the fire hose of location updates. But the actual rider-driver matching, that uses custom systems, likely involving RPC for direct, fast coordination.
So Kafka for ingestion, something else for core logic.
Right. And their real-time customer chat uses WebSockets to talk to browsers, GraphQL subscriptions for server updates, and then Kafka again on the back end to connect the microservices involved.
A real toolbox approach.
Exactly. Pick the best tool for each specific part of the problem.
And cloud events in practice.
Yeah, like in Google Cloud Run. An event trigger, like a file upload, delivers data to your function wrapped in a cloud event. Your function code just deals with the standard envelope. Makes functions more portable. CNCF projects like Dapper and Native are pushing this heavily. Companies are processing hundreds of millions of these daily now.
So the lesson is, avoid putting all your eggs in one protocol basket.
That's often the reality in mature, complex systems. Build a polyglot messaging platform. Have Kafka, maybe RabbitMQ, maybe NATs, maybe RPC in your toolbox. Use abstractions in your code to hide the specifics where possible.
Okay, but no tool is perfect.
Yeah.
Let's talk limitations, challenges. What are the catches for each protocol?
Absolutely. Architects need to know the downsides.
Can be complex.
Yeah.
That 0.9.1 versus 1.0 split is confusing. Can be seen as heavyweight, higher operational overhead compared to some others.
MQTT.
MQTT doesn't have native tailored encryption, relies on TLS. Flexible topics are great, but can lead to chaos without good governance. Schema on read. Reliability guarantees, QS1-2, need careful broker configuration, sessions retention to actually work as expected.
Stomp. Yeah.
Often too simple, lacks advanced routing, transactions. Text-based means lower performance than binary options. Kafka. The partition log model makes elasticity hard. Repartitioning is a complex, disruptive operation. Managing schemas, data governance, discoverability at enterprise scale are a big challenge.
NATs, especially Jetstream.
NAT is Jetstream. Doesn't guarantee ordering across multiple consumers of the same subject. Unlike Kafka's per-partition ordering, there are known anti-patterns, like too many consumers, or certain filter types that can hurt stability.
And ZeroMQ, the library.
ZeroMQ. Biggest limitation is it offloads all reliability to you, the developer. It will drop messages if subscribers aren't ready. You have to build persistence, discovery, etc. Debugging can be hard. You can sometimes crash processes in weird ways.
So clearly, messaging isn't a solved problem. Still challenges.
Far from solved.
Yeah.
Theoretically, things like optimal routing and consensus are still active research. Practically, achieving truly generic exactly when processing across different types of systems, queues, databases, APIs, is incredibly hard.
And the CIP theorem?
Always there. Consistency, availability, partition tolerance, you still have to pick your trade-offs.
Yeah.
And as systems scale, just understanding what's happening, observability, data lineage, governance becomes a massive challenge in itself.
This has been incredibly thorough. So for that senior architect listening, facing these choices, what's the final takeaway, the recommendations?
It always comes down to your specific needs.
Yeah.
You need a framework, ask the key questions.
Reliability, best effort, at least once. Exactly once. That narrows it down fast.
Okay.
2, performance profile. Need crazy throughput, Kafka. Ultra low latency, ZeroMQ and NATs core. Balanced, RabbitMQ, NATs, Jetstream. 3, ordering needs. Strict order per key, Kafka. Or is best effort okay?
Got it.
4, operational model. Got a team to run complex brokers. Prefer managed cloud services. Or willing to put reliability logic in the application code, ZeroMQ.
And 5th.
5, ecosystem building for IoT, MQTT. Web UIs, WebSockets, maybe Stone, need interoperability across many systems, AMQP, MQTT, cloud events.
That's a great checklist. So the ultimate wisdom for an architect here.
I'd say it's architectural humility. Recognize that the landscape will change, technologies evolve, your requirements might shift.
So, design for change.
Exactly. The single most important thing you can do is isolate your messaging infrastructure behind a well-defined abstraction layer in your code. Don't let your core business logic depend directly on Kafka Python or Pika or whatever library.
An anti-corruption layer.
Perfect term for it. Your code talks to your own event publisher or task queue interface. Behind that interface, you can swap out Kafka for RabbitMQ or Nats for a cloud service with minimal disruption to the rest of your system.
Gives you agility, avoids lock-in.
Huge long-term benefit. It's an investment in future flexibility that almost always pays off.
Fantastic advice. And that, I think, wraps up our really deep dive into the world of messaging protocols. We've gone from async basics all the way through AMQP, MQTT, Kafka, Nats, ZeroMQ. Covered a lot of ground.
Yeah, how they underpin so much of modern distributed systems.
We hit the trade-offs, performance versus reliability, looked at real-world examples from Netflix and Uber, even peeked at the future with QUIC and CloudEvents. It really highlights the joy of architecture, seeing how these pieces fit, right?
Absolutely. Seeing the patterns and the different philosophies is fascinating.
So what stands out to you, our listener, from today? Maybe that critical difference between an event log and a work queue. Or perhaps that final thought on architectural humility and designing for change.
Lots to think about.
We really hope this deep dive gives you that shortcut, makes you feel well-informed on such a critical topic. Thanks so much for joining us today on The Deep Dive.
Thanks for listening.
And make sure you subscribe to Joy of Architecture so you don't miss future episodes where we keep exploring the fascinating world of system design.